Have you ever wondered how such a common material as sand can be transformed into glass, present in windows, bottles, screens, and hundreds of objects we use every day? Behind that transparency and strength lies an impressive industrial process that combines science, engineering, and extreme temperatures, from the extraction of silica sand to its conversion into glass sheets ready to be shipped worldwide. Although glass may seem fragile at first glance, its properties can be surprising. Thanks to strengthening and heat treatment techniques, this material can withstand very high temperatures without losing its shape or integrity, as well as resist heavy pressure and intense impacts. Processes such as tempering increase its mechanical resistance up to 5 times more than that of ordinary glass, making it ideal for facades, doors, and safety barriers. Laminating, on the other hand, combines several layers joined by a plastic sheet, allowing it to remain in one piece even after an impact, preventing the dispersion of dangerous fragments. Glass is not a recent invention. The first evidence of its use dates back to around 3000 BC, when it was accidentally discovered in ancient Egypt. According to historical records, the discovery occurred when silica-rich sand was heated together with sodium carbonate near a fire. The extreme heat caused the mixture to melt and solidify, producing a translucent, shiny material. In its beginnings, glass was mainly used as a decorative element. Craftsmen shaped it into beads, pendants, and small ornamental objects. Over time, production techniques evolved, and by the late 19th century, brighter, clearer, and more uniform glass was being made. However, production remained expensive and inefficient. A turning point came in 1959, when British engineer Alistair Pilkington developed the so-called float glass process. This system revolutionized the industry, as it allowed flat glass to be produced continuously by floating molten glass on a layer of liquid tin. Thanks to this innovation, it became possible to obtain perfectly smooth, transparent surfaces, manufactured on a large scale and at a much lower cost than before. The essential component of glass is silica sand, a material very abundant in the Earth's crust. However, not all sand is suitable for this purpose. The one used must have very high purity and a minimal content of impurities. In some regions, such as certain mining areas of Brazil, silica sand deposits are not found on the surface, but in deep veins within hard rock. To access them, mining techniques involving drilling and the use of explosives are employed. The procedure begins by drilling holes about 11 meters deep, into which charges composed mainly of a mixture of ammonium nitrate and fuel are placed. This type of explosive is powerful and relatively easy to handle. Each main charge is accompanied by a secondary, more sensitive detonating charge, ensuring the explosion occurs in a controlled and effective manner. Once everything is prepared, the blasting supervisor gives the order to detonate. The explosion fractures the rock and releases huge quantities of silica sand. After waiting for the dust to settle, excavators go into action, collecting the material and loading it into high-capacity trucks. In a matter of hours, thousands of tons can be extracted, which are then transported to the processing plant. Silica sand, as it is extracted from the mine, cannot be used directly in glass manufacturing. Although its composition is mostly silicon dioxide, it contains a significant proportion of impurities that must be removed to ensure the quality of the final product. These impurities include clay particles, unwanted mineral fragments, organic remains, and occasionally small amounts of metallic oxides that can alter the color and strength of the glass. The first step in purifying it takes place at the processing plant, where the sand undergoes intensive washing. This process is carried out in large steel or concrete tanks, designed to withstand both the abrasion of the material and the high temperatures of the water. There, the sand is mixed with hot water and, in some cases, mild chemical additives that help dissolve clay compounds. Controlled agitation inside these tanks is essential. Mechanical paddles or air bubbling systems move the material continuously, ensuring unwanted particles detach from each grain of sand. The water, now loaded with sediments and organic matter, passes through a filtration and settling system that separates impurities and allows the liquid to be reused, reducing resource consumption. Once washing is complete, the wet sand is moved to the industrial drying stage. This step is carried out in large-scale dryers that use controlled temperature hot air currents to remove all traces of moisture. Drying not only prevents problems during melting, such as bubble formation or dangerous splashes, but also preserves the material's chemical purity. When the drying process is finished, the sand, now clean and ready for use, is temporarily stored or packed into high-capacity bags, generally weighing 1 ton, reinforced to withstand transport. These bags are prepared to be shipped directly to glass factories, where the next phase begins, mixing with other components to start the melting process. At one of the largest glass plants in the United States, the process begins with the weekly arrival of more than 5,000 tons of high-purity silica sand. The material is unloaded into protected silos, where it remains sheltered from moisture and impurities until the moment of use. To transform it into glass, the sand is combined with other essential ingredients. Sodium carbonate acts as a flux, reducing the temperature needed to melt the silica and thereby decreasing energy consumption. Calcium carbonate, in turn, improves the mechanical and chemical resistance of the final product, making it more stable against impacts and thermal changes. A key component in the modern formula is recycled glass, or cullet, coming from offcuts and defective pieces from previous batches. Since it has already been pre-melted, it accelerates melting and allows more efficient energy use, as well as reducing environmental impact. If colored glass is desired, precisely measured metallic pigments are added. Cobalt oxide, for example, produces an intense blue. Iron oxide yields greens, and other compounds make it possible to obtain anything from subtle shades to opaque and decorative finishes. All these components are poured into a dual-chamber industrial mixer equipped with paddles and agitators that work in sync to achieve a homogeneous mixture. Uniformity in composition is essential to avoid imperfections, bubbles or weak areas in the pieces that will later be produced. After mixing all the components, silica sand, sodium carbonate, calcium carbonate, recycled glass, and pigments when needed, the batch is sent to the main furnace. This industrial equipment, fueled by natural gas, can reach temperatures close to 1,650 degrees Celsius, far hotter than volcanic lava. Its interior is lined with refractory materials that withstand constant heat without degrading, maintaining process efficiency and safety. Due to the extreme conditions, workers near the furnace wear fire-resistant suits with layers of aramid fiber, reflective aluminum, thermal gloves, and face shields, allowing them to endure the heat radiation and hot air. The furnace is charged using large-capacity crucibles capable of holding and heating the mixture in a controlled way. Once the material is introduced, the opening is closed to preserve the temperature and maintain a stable atmosphere inside, ensuring uniform melting. During the process, long metal tools are used to stir the molten glass, releasing air bubbles formed during melting. Even small bubbles can reduce the glass's transparency and strength, so removing them is essential. Melting continues for 24 hours or more, enough time for all the components to integrate into a viscous, shiny mass. Only when it reaches the necessary homogeneity, viscosity and purity is the glass ready for the handling and forming stage. When the glass has reached the right temperature and consistency inside the crucible, the extraction phase begins. This work requires speed and precision as the material starts to cool as soon as it leaves the furnace. The operation is carried out with special metal ladles made from heat-resistant alloys, with capacities ranging from 2 to 18 kilograms, depending on the size of the piece to be produced. In some designs, especially decorative ones, several ladles of glass in different colors are poured onto the same work table. These colors are obtained with metallic pigments added during melting and must be handled carefully. Too much mixing dilutes the tones, while precise handling produces defined, attractive patterns. The skill of the operators is key at this stage. Using stainless steel tools, they distribute the molten mass evenly, maintaining color intensity and preventing uneven cooling. Next, the glass passes through a roller machine that flattens it into thin uniform sheets. Controlled pressure and the right temperature remove air bubbles and ensure a smooth surface. Finally, the sheets are placed in an annealing furnace, where they cool gradually. This process is essential to release internal stresses and prevent the glass from cracking or warping. Annealing time varies depending on the thickness and type of glass, ensuring that each piece retains its strength and stability before moving to the next production stages. When the sheets have completed gradual cooling in the annealing furnace and reach room temperature, they are moved to the cutting section. This area combines precision machinery with operator expertise, as any error can ruin an entire piece. To mark the cutting lines, tools with tungsten carbide tips, an extremely hard material, are used, allowing fine, continuous incisions on the glass without causing uncontrolled fractures. These marks do not cut immediately, but create a weakening line, along which the piece will break cleanly with slight pressure. The cut may be in standard or custom measurements. On average, one crucible produces about 25 sheets a day, while a furnace with several crucibles can exceed 300 units daily. The freshly exposed edges are extremely sharp, so operators wear resistant gloves and protective clothing. In many cases, pieces undergo edge polishing or beveling to smooth them, especially if the glass will be used in visible or direct contact applications. Leftover fragments are not wasted, they are crushed and reintroduced into the process as recycled glass, reducing raw material consumption and energy use, since this material melts at lower temperatures than pure sand. Finally, the pieces are inspected for defects and packed in reinforced wooden crates or metal frames with separators and padding, preventing them from colliding during transport. Thus, they are ready to be shipped worldwide, where they will become windows, doors, screens, or architectural elements that form part of daily life. Each glass sheet, perfectly cut and packed, is ready to begin a new production cycle in the hands of manufacturers and designers. Its destination can vary widely, becoming windows that light up homes and buildings, part of windshields and vehicle windows, integrated into electronic device screens, or transformed into panels, furniture, and decorative elements. Each piece is the result of a precise journey, extracting high-purity silica sand, cleaning it to remove impurities, mixing it with additives that improve its properties, melting it in extreme temperature furnaces, and molding it to achieve the desired shape and thickness. What began as simple grains of sand, thanks to engineering and rigorous quality control, becomes a key material in modern life. Its transparency, strength, and versatility make glass present in sectors as diverse as construction, transportation, technology, and everyday use, adapting to functions ranging from the functional to the aesthetic.